In machine learning, it is not only critical to apply correct technique to solve a given problem, but also important to know, for best results, what not to use. There is a compact method for linear regression which doesn't need us to run an optimization algorithm with derivative to find parameters of the linear regression equation. By algebraically solving the normal equation, we can obtain the results, that is, the parameters. And yet, for many real-world practical problems that have large data sets, we cannot use the method of the normal equation. It is good to be aware of this method so that we know when to apply it and when not to. In this video, I will introduce the normal equation, solve the normal equation for an example dataset by hand, and compare our results with those of a Python implementation of the normal equation. We will then discuss the conditions under which the normal equation should not be used. First, let's introduce the normal equation, which we will use to solve our linear regression problem. In linear regression, our objective is to fit a regression line to our set of observations or data points or examples. We calculate parameters of the equation of this line so that the parameters minimize a specific cost function. By minimizing the cost function, we optimize the error of fit of our line to the observations or examples. We're going to use 3 examples and 1 variable. So for 3 examples are observations in 1 variable, which we designate x1, linear regression equation in vectorized form. Where theta is the vector of parameters or parameter weights. The vectorized form of the equation can also be written as y hat is the function represented by this linear regression equation. In our case, since we have 1 variable x1, the linear regression equation becomes equation in 1 variable. The normal equation is represented by theta equals inverse of the whole thing of x transpose dot x transpose dot y, where x is the matrix of x values of observations or examples, and y is the vector of corresponding y values. We will refer to our matrix of x values as features. And vector of y as labels. Next, we will compute the components of the right-hand side of the normal equation using matrices and determinants. First, the transpose of x where x equals xt equals dot product of x transpose and x. Next, we need to calculate the inverse of the whole thing of x transpose dot x. Inverse of a matrix A is given by Therefore, the inverse of the whole thing of x transpose dot x evaluates to Now we're ready to plug in the various components in the right-hand side of the normal equation. Solving for theta hat theta 0 equals theta 1 equals. With theta values, that is, parameter weights calculated, we can plug in the theta values in our linear regression equation. Y hat equal to theta 0 plus theta 1 times x1. So this is our solution for the linear regression equation by hand using algebraic method and the normal equation. Let's now compare our results with the output of a short Python program that implements the normal equation. Note, I'm using Python 3. I'm using the NumPy library for my implementation. I define the x values here. Here is how it maps to the matrix of x values I used in my hand calculation. Y values are defined here. It maps to the vector of y values in my hand calculation. This line here implements the normal equation and solves for theta. I'm printing the theta 0 and theta 1 values computed by the Python program. The values do line up with those in my hand calculations. However, theta 1 has a slight difference. This line here computes the wall clock time taken by the Python program to process the normal equation and calculate theta. We can see that it took us about 0.03 seconds on my laptop to solve theta for our small 2x2 matrix of features, or x values. This does not seem a terribly long time to solve our equation. However, remember that our normal equation requires us to invert the whole thing of x transpose dot x, which is a n by n matrix. n is equal to 2 in our example. The numerical computational complexity of inverting this n by n matrix is of the order between n to the power 2.4 and n to the power 3. If we double our number of features, the computation time is multiplied by approximately between 5.3 and 8, theoretically speaking. Herein lies the main issue of not being able to use the normal equation for a large number of features. Theoretically, the computation for normal equation for very large feature sets, that is, very large n, becomes too slow for practical use. But in my experience, I found the time taken varies based on the data type and size combinations of features. Let me know in the comments box what kind of features versus computation times you experience in your implementations. That brings us to the end of this video. In summary, we reviewed the normal equation as an option for solving linear regression equations and the limitation of normal function in solving linear regression with very large features.